Might get the little pop-up thing. And yeah, Erin, you can go ahead and kick us off with the first problem. Today, we are going to be going over a little bit of like complexity and a lot of graph stuff. So make sure you watch those videos that Ada posted and go through the reading, because I don't think we had an official lecture.
Yeah, today there's no definitions or anything either. We'll just start with the first question. So our first question is bits and pieces. We want to determine which of the following problems can be computed in worst case polynomial time, O to the n to the k for some k, where n denotes our number of bits in the binary representation of our input. So I'm just going to go over this for a sec. So we want O to the n to the k, where n is our number of bits. A little n is our number of bits, and our input is a big N. And then so like by doing math, our little n is equivalent to log of our big N, and our big N is 2 to the n. So an example like of an input we could have is like 8. Its binary representation would be like 1000. So we would have 4 bits. So we want to determine if each of the following questions, 1, 2, and 3, which of the problems can be solved in polynomial time, and if it can be solved in polynomial time, give an algorithm and explain briefly why it is polytime. And if we think the problem cannot be solved in polytime, then we provide explanation why. So our first problem is we want to determine an algorithm that given an input n, outputs n factorial. So does anyone have any first thoughts on if this is polynomial or can be done in polynomial time or not? If you don't want to talk today, you can feel free to put it in chat.
So you don't have to come up with an algorithm on the spot. Just give a yes or no hunch. Yes, do you think it can be done in polynomial time in terms of the number of bits? Or no, you think n factorial is pretty big and it can't be done in polynomial time?
I see one yes change to oh wait. Yeah, so actually this can't be done in polynomial time because n factorial, in order to write down or return n factorial, we would need log of n factorial bits, which is already O of n, big N, like O of n log n. And this part here is in the textbook. Its reference number is at B1726. So when we look at this, like we already see a big N here, which is already 2 to the n. So this is exponential. Just writing down like our n factorial would be exponential in terms of the number of bits. So 1 can't be done in polynomial time. So what about 2? 2, we're given an input n, and we want to output if n is equivalent to m factorial for some positive integer m. First thoughts on if we could be able to calculate this in polynomial time or not. For any m. Yeah, we just want to check like if there exists for some positive integer m, if n is equal to m factorial. So for any m, yeah.
So instead of actually finding n factorial, we're checking if n is equal to something factorial. So you can hit just yes or no if you don't want to write it down. So yes, do you think this can be done in polytime, or no, you think it cannot be done?
Yeah, and you can do that in a participants tab too. Any first thoughts? Any guesses?
So think about how we changed the problem. So instead of, we started off with an input n in the first one, and we had to turn it into n factorial. Now we're starting off with the input n, and we aren't factorializing it. We're checking whether itself was equal to something else smaller factorial. Okay, so we have 3 yeses.
Yeah, so we have a couple yeses here, and the answer is yes. We can write an algorithm for this. So we could essentially just iteratively calculate our factorial and check. So we like start off with our starting variables, and then while x is less than or equal to our big N, x is equal to m times x, and m equals m plus 1. Afterwards, if x equals n, we return true. and else we return false. So like from just looking at it, we can see that it will calculate if n is equivalent to some m factorial, because if we just check x all the way until it like becomes either greater or equal to n. So if it was equivalent, then we know that n is equal to some m factorial, and if it's not, we return false. So now like let's analyze the time complexity of this. So in this step here, we're multiplying x by greater or equal to 2 past the first iteration, which means that with this while loop will only last at most log of n iterations. Like this is like a really crude upper bound, but this is just an upper bound that like it's easy to see, and it's all we need to show that it would be polytime with respect to the number of bits. And the other most expensive operation within our while loop is the multiplication of m and x, which from our naive multiplication algorithm takes log of n squared, which means that overall our whole algorithm would be O of log of n cubed, which is O of our little n cubed, which means that this is polytime with respect to our input.
So are there any questions on
why?
why the runtime was that? Like why the number of iterations was that? Why anything took a certain amount of time? What the algorithm is doing?
The iterations part? Yeah, so for the iterations part, like we multiply, when we try to get to like n from like log of n, like we would be like 2 times 2 times 2 times 2 log of n times. And then we would get, if we multiply by 2 each times, like we would have log of n iterations, since our big N is equivalent to 2 to the little n. But when we're doing this factorial, we're actually multiplying by like 1 times 2 times 3 times 4, all the way until the whole result also hits log of n. And since we're multiplying by at least 2 in each step, we know that it's bounded by, at maximum, we would have log of n iterations.
Just to say it in another way, if you're asking how many times does this while loop iterate, another way of saying that is how many times can I multiply this number x that I'm kind of gradually building up bigger and bigger? How many times can I multiply it by 2 before it gets bigger than n? And I can only multiply it by 2 log n times before it exceeds n.
Mm-hmm. Yeah. Does anyone have other questions? Yeah, n is just an integer. Okay.
Well, positive integer. So yeah, it's
positive.
a natural number, but not 0.
Okay. So our third question is, if given an input, our n, big N again, we want to check if n is equivalent to m squared for some positive integer m. Does anyone have first thoughts on if we could calculate this in polytime or not?
Just to be clear, that's not a 2n, right? That's a question mark.
Yeah, that's a question mark. Yeah.
So our previous question was asking, is n equal to something factorial? This one is asking, is n equal to something squared? Is it a perfect square?
So, no, we can't just iteratively go through it this time, because like if we checked n equals 1 squared, then 2 squared, then 3 squared, we would need to go all the way up to like root n, and this takes root n iterations, which is like 2 to the n over 2 for our small n, because it's like n to the half. So like we won't be able to calculate iteratively, but is there any other way that we could calculate this?
So notice in the sequence that Aaron wrote down, 1, 2, 3, we were like just trying to find which one it's equal to. Think back to your other classes, like 122 or something. What are some smarter ways to go through a search space rather than just like linearly searching through it?
Yeah, binary search, exactly. So we have our algorithm n, we have like our lower bound and our upper bound. And while our lower bound is less than our upper bound, our middle is equal to lower plus upper bound over 2. If m squared equals n, return true. If m squared is less than n, then our lower bound equals m. If m squared is greater than n, then our upper bound is m. And after our whole while loop, if we weren't able to find a matching m, then we'd return false. So this is just binary search to find if there exists an m that will be equivalent to n. And its time complexity, again, we're decreasing the range here by half each time. So this will also have log n rounds. And for again, our multiplication, if we use our naive multiplication, it's again log of n squared. So overall, it's O of log of n cubed, which is in O of our little n cubed, which is again polytime. Yeah, so like it literally won't work, but binary search makes it log time, so it works. Does anyone have any questions?
Cool. So the key takeaways from this problem are, one, keeping in mind that now we're doing polynomial time in terms of the number of bits instead of the input. So I think in a lot of classes we're used to considering big O in terms of the input. Now you switch to number of bits.
Mm-hmm. So I have just one question about explaining the log of n squared part. So this is just like from naive multiplication, when you like are doing your multiplication and like you do every bit, like it will take log of n is like the number of bits and it will be squared. Like this is our just our naive way of just doing multiplication with the number of bits. Yeah. Okay.
And we know m is always going to be in between low and high. So the biggest m could possibly be is n. So that's why it's bounded by log n when we multiply m by itself. Cool. I am going to share my screen and we are switching gears into graph theory. All right, so can everyone see that?
Yep.
Okay, so I highly recommend that you go watch the video and read the notes for the section on graph theory, but just to do a little recap, as we're doing the problems, we'll go through some of the definitions and proofs from the notes. So the first thing is this problem clearly correct. So it says that a connected graph with no cycles is a tree. Consider the following claim and proof that any graph with n vertices and n minus 1 edges is a tree. So before we get into the proof, let's go over what this is actually saying. So from the notes, remember that the definition of a tree is any graph that satisfies at least 2 of the 3 properties. It is connected, it has no cycles, aka acyclic, and the number of edges m is equal to the number of vertices n minus 1. So as long as you satisfy 2 of these, having any 2 of them will actually imply the third one. And the proof of how each pair of these imply the third one is in the notes, and I highly recommend you go through that. There's a lot of cute graph properties in those proofs that you might use later in the homework and other problems we give you. Okay, so that's the definition of a tree. But somehow this proof is claiming that actually, if you've got n vertices and n minus 1 edges, in other words, if you only satisfy this one, then you're a tree. So right off the bat, we know this has got to be wrong because a tree has to satisfy at least 2 of these properties. But let's go through the proof and see why they think this incorrect property is true. So the proof is trying to do this via induction. So induction on graphs is kind of tricky, so let's walk through it. So they start off by saying, okay, we're going by induction. The claim is clearly true for n equals 1 and n equals 2. So they started off with their base cases. And their base cases for n equals 1 and n equals 2, well, if we consider the graph with 1 vertex and 0 edges, well, only one of those exists and it's definitely a tree. And if we consider the graph with 2 vertices and 1 edge, there's only one such graph and that is also a tree. So all right, the base cases seem pretty legit. Then the next thing they do is suppose the claim holds for n equals k. So this is their induction hypothesis. So they're assuming that for graphs of size k, that having k minus 1 edges implies that you're a tree. So that's what they assumed in their induction hypothesis. Now, in their induction step, they are starting with a graph of k vertices and k minus 1 edges. They cite the induction hypothesis on that graph. All right, so we've got this graph G. We don't really know what it looks like, so a lot of times you'll see we draw this schematic of like, okay, it's a graph. It's got stuff going on in it. Just draw a circle. This graph has k vertices and k minus 1 edges. By our induction hypothesis, we can cite this and say that, all right, G is a tree. Since it's a tree, and by definition, it must be connected since it's a tree. Now we're going to add a new vertex to G. So we create a new graph G prime with k plus 1 vertices and k edges by adding a new vertex V. So this is our graph G. We're going to add a vertex sticking out V and call this new extended graph G prime. So G prime, since we just added one edge and we added one vertex, G prime has k plus 1 vertices and it has k edges. Okay, so the new vertex we added is a leaf, so that means it doesn't create any new cycles. Also, since G was connected, G prime is also connected. And that means G prime is connected and it doesn't have any cycles. So G prime must be a tree. So by induction, it must be the case that this proof holds, and somehow just satisfying one of these properties made it a tree. So it seems okay, but there must be something wrong here. So stop and think for a second. Can you come up with the counterexample? Can you think of a graph that has n vertices and n minus 1 edges, but is not a tree? Because that'll like really prove that this proof is wrong. Okay, so there's a couple of different graphs you could come up with to follow like in the veins of the proof. Let's say our graph G, this is a graph with 3 vertices and 2 edges. So now we have to come up with a graph that has 4 vertices and 3 edges. So in other words, we're creating our G prime. And the way I'm going to do this is I'm going to add my 4th vertex and I'm going to add my 3rd edge. Ta-da! And you don't have a tree. So here's a counterexample of where we have a G prime that has k plus 1 vertices and has k edges, but G prime is not a tree. So why did our induction proof not catch this counterexample? So where it went wrong is really we started with our small graph G. We did some action to get to our big graph G prime. And the reason we did this was because we wanted to cite our IH on the small graph, and then somehow we wanted to show that the property still held in the big graph. The issue with this is that in general for graphs, it's hard to go from the small case to the big case. So this is what we're normally used to in induction, like when you did summation induction proofs and concepts and stuff like that. Normally we started with the small thing and then we did some algebra to get to the big thing. But now when we're dealing with graphs, there normally isn't some simple algebra that we can use to get from the small graph to the big graph. In general, it's really hard to predict all the different ways that you could get from the small graph to the big graph. Like we just saw here, this proof was assuming that the only way to get from a small graph to a big graph was by adding a leaf like this. But as we already saw, there's a lot of different ways that you could be adding nodes and vertices to get to a big graph. So in general, unless you're confident that somehow you can enumerate all possible ways to get from the small graph to the big graph, instead, we would recommend that you don't do that. And since we want to show that something is true for all arbitrary big graphs, we'll go ahead and start off with that. So we start off with an arbitrary, that's the important part, arbitrary big graph. We're going to take a very specific action to get to a small graph. And on this small graph, so we take a specific action. On the small graph, we can go ahead and cite the IH. And since we took a specified action to get to the small graph, we can go ahead and undo that specified action and show that whatever property we cited on the small graph still holds in the big graph. So it might seem a little bit more roundabout. You're like, why are you going big to small and then back to big? But the reason is so that we avoid this issue of having to enumerate all possible ways from getting to the small graph to all possible big graphs, because our goal is to show it for an arbitrary big graph. So that's like a way of visualizing it. Let's actually go through the general steps that you'll need for doing graph induction. So in general, you want to show that all graphs with property A have property B. So you're going to start off with your base case, and normally that's pretty straightforward. Then in your induction hypothesis, you're going to assume that having property A implies property B for all graphs of less than or equal to k vertices. And then here's the important part. Now we can consider an arbitrary graph of k plus 1 vertices that has property A. And we wouldn't be able to do this if we did it the other way. Now we get to start with an arbitrary big graph of k plus 1 vertices. Then you're going to take some specified action and remove vertices to get to a smaller graph. So now we've got to show that the smaller graph also satisfies property A. And once you show that the smaller graph also satisfies property A, then you can go ahead and cite your IH on the smaller one and assume that A implies B, so the smaller graph also satisfies B. Now that you know that the smaller one satisfies B, you can go ahead and reconstruct the bigger graph, the k plus 1 node graph, undoing whatever thing you did to make it smaller, and argue that property B is still maintained. So I highlighted two parts because this is normally the parts of the proof that require the most thought. They might have some casework. That's where the meat of the proof is. So if this hasn't completely sunk in yet, we're going to go through these general steps using an example and actually do a graph induction example. Yeah, so if you have any questions, I think you can go ahead and just put them in the chat because Erin will be looking at that. Okay, so let's go ahead and actually do a graph induction example. So give two proofs, one using induction and another using degree counting. So we'll do the degree counting one after this. For the following claim, the number of leaves in a tree with n greater than or equal to 2 vertices is going to be 2 plus the summation of all the vertices whose degree is greater than or equal to 3, their degree minus 2. So to make sure we're clear, our property, like whenever we're doing induction proofs, we normally want to show that all graphs with property A have property B. Our property A is that your graph is a tree with n greater than or equal to 2 vertices. And our property B is that the number of leaves, so let's call that L, is that the number of leaves is equal to this summation. So we want to show that A implies B for all graphs of, for all graphs. So our base case is going to be starting off with n equals 2 because property A says n greater than or equal to 2 vertices. So once again, there's only one tree with 2 vertices in it. And now we just check. What is the number of leaves? In this graph, the number of leaves is 2. And if we do the summation, 2 plus the sum over all the vertices who have degree 3 or more. Well, summing over all none of them, there are no vertices in this graph with degree 3 or greater. So 2 plus 0 is 2. So we have 2 leaves and the summation is equal to 2. So the base case checks out. Okay, so now for our induction hypothesis, we are going to assume that A implies B for all graphs with less than or equal to k vertices for some k greater than or equal to 2. Another way of saying this is assume that for all trees with k vertices, that the number of leaves in those trees is equal to this whole summation right here. Okay, now for our induction step. Once again, now we're going to start with an arbitrary graph of size k plus 1. That satisfies property A. So consider arbitrary graph of size k plus 1 that satisfies A. So if it satisfies A, in other words, it's got greater than or equal to 2 vertices and it is a tree. So since it's a tree, let's go ahead and call it T. So since T is a tree and it's got at least 3 vertices in it, since it has exactly k plus 1 vertices in it, it's guaranteed to have a leaf. Since it's guaranteed to have a leaf, we can go ahead and draw a little schematic for T. So T has got a bunch of vertices and edges and whatnot going on. It's got at least one leaf. Let's call this leaf W. And by definition, a leaf is only connected to one other node in the graph. So let's call this one S. So this is our arbitrary graph, our big graph of size k plus 1. So now we want to take a specified action to get it down to a graph of size k on which we can cite our induction hypothesis. So because we know it's a tree and it's guaranteed to have a leaf, an easy step we can take is, all right, let's go ahead and chop off that leaf. If we chop off that leaf, then this remaining graph, let's call that T prime. That's our small graph here. And to make it clear for the proof going forward, when I'm referring to S in T prime, I'm going to call it S prime. And when I'm referring to S in T, I'm just going to call it S. So the next step in our general steps of doing a graph induction proof is to show that property A still holds on the smaller graph. So in other words, we want to show that T prime is still a tree with n greater than or equal to 2 vertices. Well, T prime has size, we just got rid of one vertex, and if T had size k plus 1, then that means T prime has size k, which means what? So we need to show one, that T prime is still a tree. And yeah, it turns out T prime is still a tree. And this is pretty easy to see because we just removed one vertex and we didn't create any cycles and we didn't disconnect the graph because we removed a leaf. So T prime is still a tree. And since it has size k, k is greater than or equal to 2, we know that T prime has greater than or equal to 2 vertices. So in other words, T prime satisfies property A, so we can go ahead and cite our IH, and by the IH, T prime satisfies property B. So that means the number of leaves in T prime is equal to the summation. Let's call the number of leaves in T prime L prime. So L prime is equal to 2 plus the summation over all the vertices. V prime will represent the vertices in T prime. And let's go ahead and make little v also little v prime to keep our notation nice and clear. So all of these vertices with degree greater than or equal to 3, we are adding up their degree minus 2, summing over that. So this is what we know by our IH. And what we really want to show is that the same summation holds, but in T. So in other words, the number of leaves in T is going to be equal to 2 plus summing over the vertices in T, not T prime. This whole summation is what we want to show. So this is normally the meat of the proof. This is where we have some casework and we have some things to consider. So when you're deciding your cases and how to go forward from the proof here, you should be thinking about, well, what steps did I take to get from my big graph to my small graph? Well, in this case, I chopped off a leaf. So the vertices I really affected were one, W, because W no longer exists. And the second is S, because I affected one of the neighbors of S. So I affected the degree of S. So I'm going to case on the degree of S because this is really going to affect, once we chopped off S's neighbor W, did S become a leaf after that? Or did it have enough other vertices and have a big enough degree that it didn't become a leaf? Because that's really what's going to affect the number of leaves going forward. So if we break this up into cases, we have case 1 is when the degree of S was equal to 2. So S is in the original tree. So in other words, the degree of S prime, once we chopped off W, is equal to 1. Visually, what this looks like is that we had S and we had W. And if the degree of S was 2, it was only connected to one other thing. So once we chopped off W, S prime was only connected to one other thing. So S prime has degree 1. In that case, we kind of compensated that we lost a leaf W, but then we gained a leaf S. So really, the number of leaves in T is equal to the number of leaves in L prime. We lost a leaf and we gained a leaf. And by the IH, we know that the number of leaves in L prime is this whole summation right here. So, oh, why can I not copy that? Handwriting. There we go, the magic of iPad writing. So we know it's equal to this whole summation right there. And this is almost what we want, but what we want is not in V prime, but rather in V. So the question is, can we go ahead and just get rid of all these primes? Is that a valid thing we can do? And it turns out it is, because when we're doing that, all we're saying is that this summation used to be iterating over all the vertices in T prime with degree greater than or equal to 3. And now I want to iterate over all the vertices in V with degree greater than or equal to 3. And notice that those two sets are exactly the same, because the only vertices we affected were S and W. And S had degree 2, W had degree 1. Neither of them showed up in the summation. So that means every single vertex in the summation is the same in both T and T prime. So we can go ahead and get rid of the primes and the equality still holds. And we've shown what we wanted to show in this case. All right, I'm pausing in case people want to put questions in the chat or unmute themselves. I know I'm like, there's a lot going on in this proof. Okay, let's go to case 2 then. So in case 2 is when the degree of S is not equal to 2, but instead it's greater than equal to 3. So what that looks like visually is that we have S, we know it was connected to W, and it's also definitely connected to more than one other thing. So when we look at S prime, it's still connected to more than one other thing. The degree of S prime, well, we don't know exactly what it is. Like in the other case, we knew it was equal to 1, but we know it's at least the degree of S minus 1, whatever the degree of S was. Now we have the issue that the number of leaves in T actually went down. We got rid of W and we didn't gain another leaf. So the number of leaves in T is 1 greater than the number of leaves in T prime. So we can go ahead, and plug in what we know from our induction hypothesis, plug in that L prime is equal to this summation right here, paste that, L prime plus 1. I'm going to go ahead and also scooch this over, give a little bit more room. The question is, can we turn this into what we want to show, which is in T instead of T prime? So in other words, if we do the same thing as before and we kind of just get rid of all the primes, is that still valid now? Not quite, because S was in this summation. S had degree greater than or equal to 3. And degree in S prime was potentially also in the summation. So when we change from S prime to S, we are affecting the terms in the summation. So let's try and compensate that. If we switch from T prime to T, and we know that we might have affected the term in the summation that has to do with the node S, we can compensate by adding back what we lost. So we lost the degree of S prime minus 2. The minus 2 is just like this summation right here, but this term in the summation for S prime. That's what we lost. And what we accidentally gained was the degree of S minus 2. So if I go ahead and add back what we lost and subtract what we accidentally added in, now the equality still holds. And the nice thing about this, maybe you've already noticed, is everything happens to cancel out now. So the minus 2 here can cancel out with the plus 2 here. This is a plus because the minus carries over. The degree of S prime we know is equal to the degree of S minus 1. So the degree of S prime will cancel out with the degree of S and with the plus 1. And all we're left with is this term right here, which is what we wanted to show. Okay, so I know that was a pretty big proof, so I'll be surprised if there are still no questions. So does anyone have questions on a step of this proof or how we decided the casework, how the summation stuff was working, anything like that? Okay, someone asked, can you explain the cases again? So I guess there's two ways to interpret this. Do you want to know why we came up with those cases, or what the cases do in the proof? Okay, how did we come up with these cases? So we came up with the cases where we case on whether the degree of S was 2 and whether the degree of S was greater than or equal to 3. And the reason we did this is because we're counting the number of leaves. So the number of leaves, how it changed when we went from T to T prime, is really that we got rid of this leaf W. And when we get rid of a leaf W, it affects 2 vertices in the graph. One, it affects W because W is gone. And it also affects W's neighbor. And W has exactly 1 neighbor because by definition, leaves have 1 neighbor. So the neighbor it affected was S. the question we have to ask is, how does that affect the number of leaves? So there's two cases. Either S became a leaf after we got rid of W, or S did not become a leaf. So case one is when S became a leaf. So this is what it looks like, that, okay, W was a leaf, S was not, but after we got rid of W, S became a leaf. And case two is when S was connected to enough other things that even after we got rid of W, S was still not a leaf. So really, you can think of our two cases as whether or not the neighbor of the leaf we removed, whether that neighbor then became a leaf or did not become a leaf. Awesome. Okay, so we're almost to there, but all we did is the induction proof. Hopefully that made sense. Keep in mind the general steps we just went through when doing this proof, how we like started off with an arbitrary graph. We showed the smaller one satisfies A, that was like this part. Then we cited the IH, and then we showed that the property was preserved. So in other words, the property was that this summation holds, and then we showed that even when you went back from T prime to T, the summation property was still preserved. Okay, so with that all in mind, now we're going to prove this all over again, but this time using a degree counting argument. So once again, please do watch the lectures and read through the notes because they'll go into more depth of different examples of this. And the number one thing you'll be using in all your degree counting arguments is something called the handshake lemma. So the handshake lemma is this nice property that says that 2 times the number of edges is equal to, if we sum up over all of our vertices, the degree of that vertex. So there's a couple of ways you can see that this property makes sense. One way to see it is that if you've got some graph, okay, so here's our graph. I'm just going to go through each vertex and do the right-hand side. So I'm going to go through each vertex and add up its degree. So if I start off with this vertex, I'm going to add 1, 2, 3. From this vertex, I'm going to add 1. Then from this vertex, I'm going to add 1. And from this vertex, oops, not 1, my bad. From this vertex, I'm going to add 1, 2. And from this vertex, I'm going to add 1, 2. So overall, I added, how much is that? 8. And we have 4 edges here, and I counted 8. And it's kind of easy to see that for every single edge, it has 2 tick marks. In other words, every edge got double counted, 1 time for each of its 2 endpoints. So hopefully that makes sense then, that when you sum up over all the degrees, you count every single edge 2 times, 1 for each of its endpoint. So this equality holds. So that's one way about thinking about the handshake lemma. There's also another way that actually has to do with handshakes, something like if a bunch of people in a room, like an even number of people shake an odd number of hands. You should go ahead and watch the lecture and see that proof of it. So that one's kind of cute and actually tells you where it gets its name from. But the point is, whenever we're doing these degree counting arguments, the general strategy is you're either going to cite the handshake lemma somewhere, or you're going to start off with the handshake lemma and do some like algebraic manipulation, some reasoning, and get it to where you want it to be. So what we want it to be is that the number of leaves in a tree with n greater than or equal to 2 vertices is equal to this summation. So we can go ahead and start off by saying like, all right, let's start off with the handshake lemma. So the sum over V. But if we start off with the handshake lemma, we don't have the number of leaves anywhere, which is really what we want to show something. We want L is equal to something. Well, a leaf is just any vertex with degree equal to 1. So let's go ahead and split up our summation to kind of introduce leaves into there. So let's split up our summation into all vertices with degree equal to 1, plus where we sum up over all V. I guess I'm kind of excluding the V and V part just so I don't have to rewrite that over and over again, but it's there. All the non-leaves. So the top summation is equal to this sum, because all we did is split it up into leaves and non-leaves. And this is really nice because we're adding 1 for every single leaf. So that's just another way of saying count the number of leaves plus all of this stuff. Just carry that down. Awesome. So now we've introduced the number of leaves in there. The second thing we might want to introduce is that in the thing we want to show, there's a -2 going on. And our thing does not have a -2. So let's go ahead and just kind of stick that in. So if I have this summation, and I just decide that I want to turn this into, or let me not erase that. What is it? Yeah, degree of v -2. I can't just put in a -2 just because I feel like it and keep this equality maintained. So in order to maintain the equality, I need to compensate for the fact that I stuck in that -2. So let's think about what I just did when I inserted that -2. For every single non-leaf, I subtracted an extra 2. So now I need to compensate and undo that. So for every single non-leaf, so n minus L, I need to add back 2 to compensate for this extra -2 that I added in. So does that make sense, where n minus L times 2 is coming from? Okay, so I'm going to go ahead and rewrite n minus L times 2. I'm just going to expand the 2 out and write 2n minus 2L, just to make it cleaner. And on the left-hand side, I also know that since we're only dealing with trees, trees have this nice property that m is equal to n minus 1. The number of edges is always equal to the number of nodes minus 1. So I can go ahead and replace m with n minus 1. So 2 times n minus 1, or in other words, 2n minus 2. So now that I've plugged in a bunch of things I know, this, maybe you're already seeing it. It gets really nice because this 2n cancels out with this 2n. And doing some algebra, I've got this -2L and this L, and I have this -2. So I'm going to go ahead and bring all the L's to the left-hand side, bring the remaining 2 to the right-hand side, plus, and then this degree whole summation just stays exactly as it was. And is this what we wanted to show? Almost there. So this looks almost exactly like what we want to show, except this has to be degree greater than or equal to 3. And right now we have a 2. So the question then becomes, can I just take this 2 and turn it into a 3? Is that valid? And it turns out this is a totally valid operation. Because think about it. All we did is from the summation, all the terms that had degree of v equal to 2, we removed them. But all the terms that had degree of v equal to 2, their term in the summation was 2 minus 2. Oops, thinking ahead of myself. 2 minus 2, which is just 0. So by turning this 2 into a 3, all I did is stop adding a bunch of zeros, which is totally fine. So you should write a description of why the 2 can just become a 3. And now we've shown what we wanted to show, that the number of leaves in a tree with n greater than or equal to 2 vertices is equal to this summation. All right, so let's stop for questions. There is, yeah, okay, we have 5 more minutes left. So in that time, there's an extra problem, but I'm not sure if we can finish the extra problem in 5 more minutes. I think it might be more useful to make sure you guys have a solid understanding of how graph induction works and how degree counting argument works. And also, I can't swipe to it because it's not on my screen, but also going over how to analyze the runtime in terms of the number of bits of an algorithm, the problem that Aaron did. So might be more useful to go over questions on those 3 problems. Someone asked, can you explain why the last operation is valid? So by last operation, you mean why is it valid for me to just turn this 2 into a 3, right? Yeah, okay. So why is it valid for me to turn the 2 into a 3? So let's do a little example and like break it down further. So if I'm summing over all the vertices with degree greater than or equal to 2, the degree of the vertex minus 2. Let's have some kind of example graph where I've got, actually, let's actually use this example graph right here. We can't use it because it's not a tree. Let me go ahead and make it a tree. There we go, this tree right here. So this tree has no vertices of degree 2, so it's going to be pretty useless for this. Let us not use this as an example. And instead, I'm just going to make up some degrees. So let's say my vertices have degrees. I don't really know if this is a valid graph or if this will work, but let's say we have one vertex with degree 1, one vertex with degree 2, and then a couple of vertices with degree 3 and one with degree 4. So the question is, can we remove things that have degree 2? So first of all, we know that if something has degree 1, it's not going to show up in the summation because we're only considering vertices of degree greater than or equal to 2. The question is, can we turn this 2 into a 3 and also ignore things that have degree 2? Well, if we look at the summation and expand it out, what this was going to be was look at each degree v and then subtract 2. So we were going to do 2 minus 2 plus 3 minus 2 plus 3 minus 2 again plus 4 minus 2. And notice, because we're subtracting 2, anything that had degree 2 was just going to be a 0 anyways. So there's no point including it in the summation. We might as well kick it off right off the bat and only include things with degree 3 or greater. Does that make sense? And then someone asked, why is there a minus 2 in the summation? So the minus 2 isn't something that we came up with. The minus 2 is really what we want to show. So we want to show that the number of leaves is equal to this summation, and this summation happens to have a minus 2 in it. As for how it got introduced into our summation, we kind of forced it in because we wanted a minus 2, and then we compensated by adding the deleted terms back in. Cool, these are all great questions. So I know graph induction is also like historically more tricky. If no one has any other questions though, I can go ahead and stop screen sharing, or I guess, Erin, if you want to mention just a bit about the last one of just what it entails, even if you don't go through the whole thing.
I could quickly. I'll share.
Yeah, just so we don't go over time,
Yeah.
I guess don't have to go through the whole thing, but
Yeah.
it's good to know about it.
So for this problem, we like want to define, we have like our big O, big omega and theta, but now we want to define like a strictly less than and strictly greater than. So like our first instinct might to be just like, oh, if I want like strictly less than, then I take like naught of my big omega. But like with functions, that doesn't necessarily work because some functions like aren't big omega, like aren't less than or equal to or greater than or equal to. Like an example is like these functions, like they actually like aren't related. Like if they're not big omega, it's still not like the other one. So like we can't just say not. So instead we have to like define it in a different way. And what we want to say is like for like little, we want to say like if f of n is little omega of g of n, that like g of n like asymptotically grows larger than f of n. So in order to do that, we need limits. So with this definition, we use like the limit as n goes infinity. And if this is equivalent to infinity, then we know that g of n like increases greater than f of n like for like asymptotically, which means that f of n is now little omega of g of n, and g of n is strictly greater than, which is we use a little omega for strictly greater than, and a little o for strictly less than. Then like this is how we can define it. It's because like we can't just take the naught. Yeah, that was like the very quick, I think I already went over time also, but the very quick explanation.
We are just on time, so this is actually perfect timing. I'm going to go ahead and stop the recording.